Thank you for the introduction. So today we want to present you our work on fast feedback control over a wireless multi-hop network. This is a joint project between researchers from control and from the communication community. So, what do future cyber-physical systems need? Well, they will cover large distances of dynamic networks, and the control and the communication task has to be solved fast and reliably. If we look at prior works, on feedback control over wireless networks, we can basically categorize them in two dimensions. First, the process dynamics, either slow or fast, or the second dimension is the network diameter, either a single hop network or a network with multiple hops. Double tank systems, for example, can be classified in this category. It's a slow physical process, usually with intervals between 1 and 10 seconds, and in this work they use a single hop network. Here, the task to do adaptive lighting in tunnels is also kind of a slow physical process with update intervals of 30 seconds, but it covers already multiple hops. And as a third example here, we have an inverted pendulum with update intervals between 5 and 60 milliseconds, but in this work they control the system over a single hop network. So this unexplored design point is our contribution, and we basically have three main contributions. We do a tight co-design of control and communication. We can come up with a stability guarantee for the overall system, and we do a real-world evaluation on a real cyber-physical testbed. So first I will talk about the co-design of communication and control. Here you can see our schema of the whole system, and we explicitly target to having multiple control over the same wireless network. Okay, so first of all, what are the key challenges that you have to face? There are many challenges, but I will focus only on three of them here. So first of all, because we use a multi-hop network, the throughput is limited compared to a single hop network. This limited throughput leads to longer end-to-end delays. Due to congestion, for example, because we have multiple control loops running, or packet losses, or simply packets taking different paths through the network, you see significant jitter on the delay. And as a third point, packet losses in the wireless network are often correlated, which is a problem on the control side. The approach to tackle these key challenges is a very tight co-design of control and communication. And we do this in two steps. The first step is to cope with these challenges at the wireless embedded system design to the extent possible. And the second step is to take these resulting key properties and account for them in the control analysis and design. Let's have a look first at the wireless embedded system design. So, how do these wireless nodes look like? We use a dual processor platform. We have an application processor, a communication processor, and they are both interconnected via a specific interconnect called both. With these two processors, we can essentially separate control-related tasks from communication-related tasks. So they do not interfere each other, and they can run in parallel. As a second point, I want to mention that with these interconnect, we have formally verified bounds on the execution times when we want to pass messages from one processor to the other processor. We can now integrate this predictable architecture into our overview, and you can imagine that each of these nodes basically is on the basis of this predictable architecture. So now how do these nodes communicate with each other? The wireless protocol that we use is based on synchronous transmissions. And I want to give you a small example how these synchronous transmissions work here. So let's assume you have this node at the bottom that has a message and that wants to send this message either to all other nodes or to one of them or a set of them, doesn't matter. So it starts first by initiating the transmission, and the other nodes that are in range, and here this will simultaneously relay the packet. So in the next step, they transmit the same packet at the same point in time. All nodes receiving this will again relay the packet, also the initiator node. So you see the transmission kind of moves through the network like a wave, for example. At this point now, the initiator transmitted 2 times. And this is a parameter that you can choose, like only transmit up to n times. Here in this example, I choose we take 2 times, and then in this case the initiator node stops transmitting. So the transmission, the packet transmission propagates through the network, and at the end, all nodes in the network had the chance to receive the packet with very high reliability. Additionally, due to nodes simply listen and repeat, so to say, we do not have any network state dependency. So we can basically support any network dynamics. And due to this fact, due to this listen and repeat kind of communication style, you also have minimal delays to get from one end to the to transmit the packet from one end to the other end of the network. A very nice property of these synchronous transmissions is that they decorrelate packet reception events. So here, in this, here we have 2 different timestamps from the previous example, and you can see that the node marked with the arrow has 2 chances to receive the packet at 2 different time instances. And it also has the chance to receive the packet by a different set of transmitters. This kind of diversity leads to a decorrelation of packet reception events, and up to the point that packet losses can be assumed IID. This has been shown empirically and theoretically in these works below. Okay, now we have seen how a single node can flood its packet into the network, but that's not very useful so far. So we have to integrate this into a wireless protocol. And this wireless protocol works in this, as a series of communication rounds. And in each communication round, you have several slots, whereas each data slot consists of such a flood that I explained to you, where one node floods a packet into the whole network. So all nodes that want to transmit a packet then have a data slot in this communication round, and they're done. After the communication round, all nodes have sent their packets, all other nodes had the chance to receive the packet, and we're done. By the nature of the synchronous transmissions, we also get a very accurate global time synchronization of the network, and that we can use to precisely schedule these communication rounds and sleep in between to save energy. Now, because we have this kind of global reference time, we can take a scheduling framework and schedule these control-related and communication-related tasks in order to minimize delays and in order to minimize the jitter on these end-to-end delays. We have shown in experiments that the jitter that you can observe is around 23 microseconds for update intervals up to 100 milliseconds. And we also computed we also showed that the theoretical worst-case jitter is -50 plus 50 microseconds. So we are well within these bounds. So taking this predictable architecture, the wireless protocol, and the scheduling framework, we can now look at the resulting key properties. And we can see that we have minimal constant end-to-end delays, we have negligible jitter, and packet losses are IID.
So now we want to take these key properties of the wireless embedded system design and look control. The jitter is negligible from a control perspective, so this we don't need to take care of. But we want to be able to control fast crystal systems. So even if the end-to-end delay is minimal, we still need to take it into account, as well as the IID packet losses. We will do this by coming up with a with a system model that incorporates all these new key challenges and then develop a controller design based on this model. So how does the model look like? We assume linear time invariant dynamics in this form with process and measurement noise. And we use a discrete time formulation. We have nearly constant update intervals. So one discrete time step here corresponds to one communication round. So the discrete time formulation is particularly suitable for our network embedded device system design. And the delay is then also incorporated into this, because delay is then exactly one discrete time step, as you can, for example, see here. So at time step k, the controller receives the measurement that was sent at time step k minus 1. We also model the packet loss in here. We know that that packet loss can be safely approximated to be IID, so we model them by independent Bernoulli random variables. Here, theta for sensor measurements and phi for control inputs. Now, as I already explained, at the time the controller receives the packet, it knows that this packet has been sent one time step in the past. So to compensate for this delay, we do a state prediction based on the mathematical model of the system. That way, the controller has an estimate of the state of the system at the current time step. In case the sensor packet, or the controller knows that in every round it should receive a packet. In case this packet doesn't arrive, it knows that this packet has been lost, and it can propagate its last estimate to compensate for the packet loss. So this can be seen in this equation. But now we also know that if we now send a control packet, this will also be delayed by one time step. So to anticipate this further delay, we do one more state prediction and then compute the control input based on the estimated state of the system by the time this input will reach the actuator. So this model and control strategy we can also write in a more compact form using augmented states. What looks like this, here without noise because of space constraints. And that way we have a very compact form to model the device embedded for the whole system, incorporating all the key properties of the wireless embedded system and also the control strategy. What we have to note here is that now the augmented state matrix A is now depends on time because the packet losses introduce time dependency into the system. So with this we can, this way we can deal with the end-to-end delay and also with the already expected losses, and this then concludes our co-design of control and wireless communication. But now we also want to have guarantees on the stability of the system, and this is what I want to show next. So first now we need to come up with a stability definition based on the system. So Z is the augmented state, A tilde the augmented state matrix. Here we do the stability analysis without noise, but we also extended this. So I'm doing this here for ease of presentation. We also extended this to the case with noise. So the noise-free system we define to be mean square stable if the state correlation vanishes as time goes to infinity. And then we can state the following theorem. So if we can rewrite the system in this form, so that means the time dependence that is caused by the packet losses can be captured by these variables pi, which need to have zero mean and bounded variance. Then we can check this LMI condition. So we need to find a positive definite p such that this LMI condition is satisfied, linear matrix inequality is satisfied. And if we are able to find such a p, then we have the guarantee that our system is mean square stable. I want to quickly give the main idea of this proof, which consists of two steps. So the first step is that we need to be able to rewrite the system that I have explained on the previous slides in this form. So as I've already said, the time dependence of our system is caused by the packet losses. So somehow the packet losses need to be covered by this variable, but we said that we will model them as Bernoulli random variables. So they will take values of either 0 or 1, and therefore clearly not have zero mean. So we transform theta in this case, which models the sensor packet losses, in this form where mu is the expected value of theta and delta is a nu, random variable. We then have that delta has zero mean and bounded variance. We know from the wireless embedded system design that theta is IID and therefore also delta is IID. We can do the same thing for lost actuator packets or control input packets by doing the same transformation for phi and delta phi. And then set P1 and P2 to these two delta variables and rewrite the system in the required form, which looks like this. And now, having the system in this form required by the theorem, we can check the linear matrix inequality, and this is a result from the theory of linear matrix inequalities. So that way, we have an easy to check condition for stability. We can, in fact, for any linear time invariant system with our wireless embedded system design and our control strategy, check whether it is stable or not.
Okay, so now we have the stability guarantee of the overall system. Let's take a look at some real-world evaluation on the real cyber-physical test bed. Maybe you have seen this yesterday, or maybe you have missed it. You will see it now in some pictures. We had a demo at IPSN yesterday, and there you could see the system in action. Okay, in our paper we have shown this test bed. First of all, the physical systems that we use here are card pole systems, and we use them as inverted pendulums. And the wireless nodes look like this. The radio on these nodes works in the sub-gigahertz band with GFSK modulation and has a data rate of 250 kilobits per second. In this test bed, we have 20 wireless nodes, and they form a 3-hop network. A and B are our physical systems, our inverted pendulums here. As a first, and yeah, that's probably the main goal of our work when we started it, we wanted to show that it is actually feasible to do fast feedback control over such a wireless multi-hop network. So the first step, we want to show multi-hop stabilization of the system. So we have these two physical systems. One of them is controlled by a controller located at node 15, and the other is controlled by a controller located at node 14. So what must happen is, or what happens here in this scenario is, these nodes sense the state of the pendulums, communicate it over the network to the controller nodes. The controller nodes compute the control input, have to send this control input back to the nodes that are connected to the pendulums, and then the control input can be applied to the pendulums. We had an update interval of 45 milliseconds in this scenario. Here you can see how the pole angle in black behaves for both pendulums over time. Here it is a time frame of 1 minute, and in red you can see the control input voltage. And as you can see, we can safely stabilize two inverted pendulums with our test in our test. I also want to show you an experiment with node mobility. I hope this works. Okay, here you can see our test bed. Here we have only one remote controller that controls both physical systems. You can see one of the pendulums here, and this is the controller node 18. In this video, Dominic picks up the node and starts moving around. As you can see, it does not have any effect on the control performance. And this is due to our wireless embedded system design, which is completely network state independent. So it does not matter where the node moves, how fast it moves in the network, it does not affect the control performance. Then we investigated how update intervals affect the control performance. Here you see the pole angle and different update intervals. So we have 4 different update intervals, and this shows the distribution of the pole angle for this specific update interval. And as you can see, with an increasing update interval, the control performance decreases because the distribution gets wider. The distribution of the pole angle gets wider. At the same time, however, you can save energy on the communication side, because a slower update interval leads to less often, leads that you have to communicate less often on the communication side. So for 20 millisecond update interval, we had around 40% radio duty cycles, and at 50 millisecond update interval. This reduced to around 17%. So how much packet losses can we tolerate? For this experiment, we artificially introduced IID packet losses, and we can see that up to 75% of packet losses can be tolerated. Again, the plot shows the same thing, pole angle distribution for different packet losses. But the more packets are lost, the longer is the distance the pendulum has to travel over the whole experiment. So now I can ask the question, what about distributed control?
That's a pretty natural question. If you do control over a wireless network, it's pretty natural to ask if you can also do distributed control. And so far we only showed how to stabilize multiple systems, but they're independent of each other. And actually, with our wireless embedded system design, it is very straightforward and pretty simple to do also distributed control. And the main reason of that is that all information that is sent by one node will be received by all others in the system. So we have full information available at every node. So what we want to do here now, to show distributed control, we have multiple physical systems that are connected over the wireless network. And now they have some common control load, some distributed control load. And as an example, we'll here look at synchronization. The systems themselves are stabilized by local controllers and share their current state over the network in order to synchronize. As I mentioned, we have full information available at every node, so therefore we can come up with a centralized design and implement it locally on each node. We define a cost function in this form, so we penalize deviations from the equilibrium state, so we still want to stabilize, and by control inputs, and also deviations from our synchronization objective, so deviations between the states. The term here in the summation can be written in this form using augmented states x tilde, and this is then in standard LQR form, and we can use it solving standard approaches for linear quadratic optimal control. And as we have the augmented state available at every node can locally solve this optimal control problem. As distributed control with two systems is not super interesting, we scale up our test bed a bit with three simulated pendulums. So we have simulations of card pull systems running on nodes 9, 14, and 15. And they exchange their state information in order to do synchronization, and the goal here is to synchronize the position of the cards. The update interval for this experiment is then 15 milliseconds. In the first experiment, we just locally stabilize all the pendulums without any synchronization tasks, and you can see that the two real pendulums, so this shows the position of the pendulums over time. You can see that the two real pendulums behave just independent of each other. The dotted lines here at 0 are the simulations. We use deterministic simulations, so they are pretty much perfectly stable. And now if we turn on synchronization, you see that all of them move in concert with the same frequency. So we're also able to do distributed control and do this in a very straightforward manner. So with this I want to conclude. In this paper we have shown tight co-design of control and wireless communication. We are able to give form stability guarantees for the overall system, and I've also presented a psychophysical test bed for real-world evaluations. And this way we also presented a solution for this design point for fast feedback control over multi-hop networks that had been unexplored before. Thank you very much.